Very happy to have Max Ayers from Rutgers. Last year I in grad school and there's this wonderful new result we'll hear about. Before we start, I just want to say a couple of reminders. So today is officially the first day of school. And there's a welcome event this afternoon. And I don't know, like remarks from the director and then some activities. At 1 p.m. we have our 1:30 p.m. we have our first members colloquium by the special year organizers. And that's it. I just want to also say that today is like the eve of Rosh Hashanah, the Jewish New Year. And I like how it aligns with the school year. So I wish you all and us all very successful school year and new beginnings. And okay, Max, the floor is yours.
Thank you for inviting me. Yeah, so the topic of our talk is balancing extensions and posets for flared width. Talking about some joint work I did with my advisor, Jeff Kahn. So I'm going to assume more or less no knowledge in linear extensions and posets. Although hopefully there will in fact not be actually zero knowledge, but I'm gonna start by literally defining a poset. So a poset for us, poset is a set P with a relation. I'm going to write the relation as you usually do. Emphasize that we have a curly relation later on. With a relation less than, which is, and it refers to a kind of important irreflexive asymmetric. But the important part is it's transitive. Underline that. Yeah, it generalizes the idea of a total order, linear order, so that not every element, every pair of elements has to actually be related. There can be some elements which you don't know, which is less than the other. But when we do know something's less than the other, it behaves about as you'd expect it to. You don't have x is less than y and y is less than x. X is less than y and y is less than z, then x is less than z. So hopefully we're actually familiar with at least what posets are. So my object of study really is a linear extension. So a linear extension, and that's what I'm going to use is curly less than a linear extension on a poset P is a total order, now a normal order, which agrees with I'll say that with relations of P. So an ordering of all the elements of P so that the elements that we already know are related are still related in the same way. So you kind of think of this as we have part of a total order, not the whole total order. And then your extension is one of the possible completions of that total order. So I'm going to do, Jeff, so we have to do this exact example because he likes it.
Is he watching?
I don't think so, but it's a good example. So if you have, I haven't said how we interpret this, but basically the things below the other things are less than those things. So this means W is less than X, Y is less than X, Y is less than Z. So what's an example of a linear extension? Well, maybe for instance, W is less than Y, is less than X, is less than Z. So we have W's before X as needed, Y before X, and Y before Z. And maybe one which isn't so obvious in this example is Y can come before Z, can come before W, can come before X. Y so before Z, Y before X, and W before X. Cool. So I'm gonna say, let's let little e of P be the number of extensions. I'm gonna write extensions for linear extensions probably from now on. So how many linear extensions are in this n poset here? Well, if y goes before w, then there are 3 spots for z. Either below the w, between w and x, or above the x. If y goes above the w, then it must go below the x, and there's 2 spots for z, below the x and above the x. So in this case, E of a poset n here equals 5. Okay, so what we care about really is what I'm going to call these comparison probabilities. So we write probability x comes before y to be the number of extensions with x coming before y over the total number of extensions. So example, in this poset here, from what I said before, what's the probability that y precedes w? Well, there were 3 extensions where y comes before w. There are 5 extensions in total, so this is 3/5. So how I'm interpreting this, this is just a question here, but I'm interpreting it as we're choosing a linear extension uniformly at random. And we're comparing the 2 elements in that uniform extension. Cool. Okay, so I'm gonna write, let the balancing constant delta of x comma y be the minimum of probability x comes before y and y probability that y comes before x. Okay, so these 2 things total 1. Obviously, this thing is less than 1/2. What do we know? So we know that if x is actually less than y in the poset, then every linear extension will have this. So that means that the balancing constant of delta x comma y will be 0. So this is some quantity between 0 and 1/2. Why do we care about this? So this is one of the big problems in computer science, or one of the big large classes of problems, I'll say, is these sorting problems where you have some linear extension and broadly you want to find it by querying comparisons. So in the model that we care about, this is called sorting under partial information. You have some poset and you want to find a linear extension of the poset, which is known by the oracle. You can ask the oracle, okay, is x less than y? And the oracle can say yes or no. And I think the general framework is what's the fewest number of comparisons that you can do this in, so that you're guaranteed to know at the end what the linear extension is. So this is what inspired this problem. It's not an exact 1-to-1 thing, but broadly based on this, what's a good first question that I can ask the oracle?
Something that cuts it in half.
Yeah, if I can find 2 elements where delta of x comma y is exactly half, that's kind of the ideal first question, because either way, like you said, I've cut the total number of extensions possible in half. So that's kind of what we want. Our goal is to find x and y so that delta of x comma y is, and I'll put large quotations for now. So if you have a chain, and every comparison is already answered. So for a chain, delta of x comma y, everything in the chain is 0. And I'm going to find, by the way, I'm going to find delta of p be the max over all x and y in the poset of delta x comma y. And maybe you want a choose x and y not together. So yeah, if you're a chain, delta of your chain is just 0. But what if you're not a chain? Well, we would hope maybe that we can find some constant lower bound on delta so that whenever you're not a chain, your delta is at least as large. And that's true. But I'm going to start with the main conjecture in this area, the 1/3, 2/3 conjecture. So if you've heard of anything about probabilities or linear extensions, you probably heard this conjecture. And that is, if P is not a chain, then we think that delta of P should be at least 1/3. So where does that 1/3 come from? We have this nice example here, where when X is less than Y, and there's an element Z. Well, how many extensions are there for this poset here? You can go less than X, between X and Y, and above Y. So there's 3 extensions. So what that means is that delta of P is going to be 1/3. So there's 1/3 probability that Z goes below X, 2/3 probability that Z goes above X. You can't pick a pair that's better than 1/3 here. So if this 1/3 exists, it's type, for this example at least. And you can come back to this a bit later, but you can stack another one of these on top of it. And this example will still be 1/3. Or you can stack just one element, which is bigger than everything here. Yeah, so 1/3 is type for an infinite family of posets, actually. That's where the 1/3 comes from. So what do we know about this question? Well, the foundational result is a theorem proved by Jeff and Saks in 1984. Does what I asked originally. It gives a constant lower bound for delta of X. Specifically, if P is not a chain, we get delta of X, Y, at least 3/11. So there's actually a consequence for this in the sorting problem I said earlier. Specifically that, well, okay, each time we can find 2 elements which aren't related, but are balanced with probability at least 3/11. So we can shave off a constant proportion of the total number of extensions. So what does this mean? This means we can sort the poset in how many queries? You do it in O of the log of the number of extensions queries. And this is obviously tied up to the constant in front, since determination theoretical lower bound is just log base 2.
This is the number of comparison, not the you're assuming of infinite
Yes.
number of
Yeah, I'll say
other calculations.
yeah, that's important actually, since at least the way he did it, there's no good way of calculating the X and Y so that delta is at least 3/11. Jeff actually found about a decade later a different algorithm which didn't find these comparisons efficiently, but found a different sequence of comparisons which also guaranteed O of log of E queries, and each comparison could be found in polynomial time. So there is an efficient way of doing this per se, but I'm going to kind of leave this model in the dark for now. What we really care about is just these balancing constants as an abstract quantity from now on. All right, so the best version of this state of the art today was proved by 3 people: Brightwell, Felsner, and Trotter. A decade later, in 95. And they showed that if P is not a chain, that implies that delta of P is at least 5 minus the square root of 5 over 10. So this is like an improvement of like 0.004 or something. It's not a very large improvement. But what's nice about this result is it's actually tight for infinite posets. I think by writing too low here. I won't talk about how you calculate probabilities on infinite posets, but there's a nice, or there at least is a way of generalizing this idea to infinite posets, and turns out there you can't do any better than this. So there is a real reason why this lower bound is going to be hard to beat. So how do they prove those two things? I'm going to just give a very brief, I'm going to say what the key idea is here. So let's let F from P to the set N. I'm going to let N be the size of P, the rest of this top. Let F from P to N be a uniform order preserving bijection. So this is just another way really of viewing a linear extension, right?
What does uniform mean?
Uniform means from all the order preserving bijections, you're picking one, each one has equal probability.
That's a randomized
Yes.
function. Okay.
Uniformly random. Yeah. Great. So I say this so that in this case, f of x is a random variable. And we can write the expected value of f of x to be some quantity h of x. So what Mike and Jeff actually showed is that if the height of x and the height of y is strictly less than 1, and that implies that delta of x and y is at least 3/11. And that right there is in fact tight. So if we know that the gap, the distance between heights is exactly 1, well, it's possible then that x is always less than y. So you can't really say anything about this probability. But if you know it's just less than 1, even only by 0.0001, well, then we can show that x and y are pretty well balanced. So this right here kind of gives a recipe to define these elements. But as I pointed out earlier, calculating these heights is, let's say, p-sharp hard.
There's always gonna be a pair that is less than 1.
Yeah, because there are, how should I say this? So this value, it can be anywhere between 1 and n, right? There's n elements, they're spread between 1 and n. The only way this doesn't happen really is if it's a chain, and one's 1, one's 2, one's 3. Any other way of doing this would be some pair that's exactly, but it's less than 1. Yeah.
So if it's exactly 1, it might be 0. If it's less than 1, there's a jump in 1.
Yeah. I think if you say that this is maybe equal to 1, but you don't have x less than y, maybe you can say something. But I'm not sure. Yeah. Okay, so that's one direction of research. This hasn't really made any advancements in the last 30 years. So if you have any ideas, let me know. But what we really care about, so our dream is kind of that delta of p should be 1/2 or near 1/2 for some x and y. As I said earlier, we can have an infinite family of linear extensions. sorry, an infinite family of posets where delta is only about 1/3. So we want to try to have some additional condition, which is still, normal or usual, but that forbids silly things like this. So let's let the width W of P be the size of a largest antichain, which is a set of elements with no comparisons or no relations between them. Yeah, so in this case, we can stack them on top of each other, but the largest antichain is still going to be width 2. Since any picking elements, one from one below, one from one above, have a relation between them. So this large width condition blocks out things like that. More generally, we have any fixed poset of finite width and stack on top of each other and get large extensions with delta not going to 1/2, but with small. So at the very least, we kind of need some condition like this if we want delta to approach 1/2. Yeah.
So sorry, going back to the previous argument, like this implication, if absolute value is less than 1, then you get the greater than or equal to 3/11. So can you say anything about how that's proved, or is that easy to prove, or like?
Yeah, like I said, I'll how this is proved. The basic idea is that you want to look at the quantity f of x minus f of y. And it turns out the key idea is that this will be log concave distributed. I don't really want to get talk about too much to abstract this, but if you use this fact and a few other maybe easier facts about probability distribution of f of x minus f of y, you show that any probability distribution which satisfies this and those must be at least 3/11. Yeah. A log concavity, this will actually be, I might talk about it at the very end if we have time. That implies a lot of what we actually do. Cool. So as I was alluding to before, this is our other conjecture, which we call the Kahn-Saks Conjecture, dating back to about that when they published that same result. And they conjectured that as the width of a poset approaches infinity, that implies that delta of the poset approaches 1/2. In other words, if we want this to be at least 1/2 minus 0.0001, there's some sufficiently large width which will guarantee that. That's the conjecture. And I think in some sense, this conjecture is actually more interesting than this conjecture. Probably the big thing here was really getting a constant lower bound. 1/3 we think might be tight just because of, this very tiny example, and computers seem to back that up, but nothing really special about 1/3 besides that. This problem is really, really interesting, and that's the main focus of our research. So I'll talk about what is known. It's a difficult problem, so there hasn't really been a lot of progress, but there are two important results. The first, I don't know where let's go with that. By Komlosh in 1990. He showed if the number of minimal elements of P is linear in N, then that implies delta P going to 1/2. So this is, the set of middle elements is a antichain. So this is like a stronger version of width. We also need to be linear, not just going to infinity. So this statement here is weaker than this one in two pretty difficult ways, or two pretty important ways. What's the second result? So this is proved by Friedman, 93. He showed that if the number of minimal elements P is little omega of square root of n, and that implies delta of P asymptotically at least 1/e. If you know anything about log and concave distributions and geometry, maybe you get a hint already whenever E would come from. But yeah, this is all that was known. So why is 1/e interesting? Well,
So 1/e is more than this.
yeah,
square root
1/e
of 5
is at least 1/3. So that's kind of where it's not good enough to get all the way to 1/2, but this at least shows that 1/3, 2/3 is true for the number of minimal elements is sufficiently large on the order of root n.
So even if the width goes to infinity, you don't know in general anything better than this 5/10 minus square root 5/10.
Correct, yeah. And still known as a matter of fact. Yeah, our first two main results are, we're gonna give a bunch of conditions which are stronger than weaker conditions than the ones Cohn-Loach and Friedman gave. They guarantee the same results. So theorem 1 from me and Jeff. You know that delta of P goes to 1/2 if. So our first condition is we are to remove the condition on minimal elements and instead just show that if the width of P is big omega of n, then that implies delta of P going to 1/2. And in particular, this means if the height of P is big O of 1, then it goes to 1/2. So I did define height. So the height's the size of the largest chain in P. So the largest set so that every two pair of elements is related. Kind of like the dual notion of antichain. Yeah, so this right here is enough to show that all height 2 posets are asymptotically balanced. We get all fixed with posets. And what's nice about that is, it's been known for a while that a random poset, under the right notion of random poset, because it's multiple one, but a random poset is almost always has height 3. So what this shows is that a random poset almost always is 1/2 balanced, or has balance going to 1/2.
What's a random poset, like how do you?
There's a couple different notions of doing it. So I think this one is, you look at a uniform poset from all the posets and n elements. Like a uniform labeled poset, maybe.
But how many comparisons are you allowing in your poset?
I think this version doesn't worry about. So just uniform from among all the
Okay.
posets. But yeah, some people, what they'll do instead is they'll pick like m different relations, and then take the transitive hull of that. Yeah. But the statement I said, but almost all posets have height 3, I believe is just for a uniformly random poset, which is a bit of a hard notion to work with. Okay, so what other conditions do we have? So if the width is linear, we are good. But also the number of minimal elements is growing faster than log of n. That implies 1/2. So that improves upon both those results, actually.
So this is 1 or 2, not 1 and 2.
Hmm?
This is 1 or 2, not 1 and 2.
Yeah, either of them
Yeah,
holds.
either, yes, any of these. Any of these conditions is sufficient. And our third condition, if the minimum height of any element in P, so the minimum h of x grows faster than 1. Maybe this is kind of like a weird condition, but what's nice about this is there's no dependence on n here. So the conditions need, as the posets get really big, these things grow to infinity as well. But this says if we want it to be, 149 balanced, we just need all the elements to have some sufficiently large height. Full stop, no dependence on n. All right. And now theorem 2. Same thing, but we can generalize the result of Joel to get at least 1 over E balanced if, and here we can generalize his result. So instead of the minimum set being width, if the width of P is omega of root n, then we are good. Also, if the height of P is little o of n. So, which is the same line since the height version is just a corollary of the width version here. But actually here, this height condition is not just a plain corollary. I mean, this one comes from this, like a Cauchy-Schwarz type argument, but yeah, this is actually pretty strong. So we only don't know this if the height is, growing linearly with the size of P. And a third condition, if the log of E of P grows faster than linear in n. So E of P can be a maximum of n factorial. So this can be at most n log n. So maybe it's not super exciting that if it grows bigger than omega of n. But one thing, this result tells us, so this result here of stacking these on top of each other, we're gonna have, we stack k on top of each other, we're gonna have E of P being 3 to the k. So in that case, log of E of P is linear, and we don't get any better than 1/3 balancing. Yeah, so there's no hope of actually getting this result for better than that. Okay. Time is it? 6 o'clock.
Until 12.
Okay, so I want to emphasize a couple of things about this. I'm going to asterisk these 3 results. So this result with this asterisk, I'm gonna say this means they're local in the sense that for this one here, an anti-chain of size omega of n must contain x and y, so that delta of x and y goes to 1/2. Kind of the difficulty with all these things is we want to show that there's two elements that are well balanced, but certainly not that any two elements are well balanced. So where do you find the balanced elements? And this is kind of the recipe to find them in all of these cases. A sufficiently big anti-chain will have 1/2 balance.
So how do you think
elements.
it goes to? I mean, you're now fixing a specific poset.
Yeah, so for a sufficiently large poset, we fix a specific anti-chain inside it. That anti-chain is linear inside the poset. Then there's two elements in that anti-chain which are balanced.
Right, but I guess you want to fix some half minus some function of n that you want to say it's within that. Was.
Yeah, so I think what you actually want to say is, like for all epsilon and gamma, there exists an n so that if the size of the poset is at least
Right.
that n, say capital N here. And if A is an anti-chain in P with A at least gamma times as of the poset, then delta is at least 1/2 minus epsilon. Yeah. And same thing here, but what's nice about this and also this, these are also locally tight. That's the difficulty. So what I mean is there are examples of posets where the number of minimal elements is log of n. For example, we can dangle off. So let's say we have a chain here, x1 through xn, and then we add a yi, which is less than x through the I. So there's a y1 that's less than x2. There's a y. Maybe we skip the x2 one. There's a y2 that's less than x4. There's a y3 that's less than x8. Something like that. Yeah, sorry. What that means is none of the minimal elements will be very well balanced. Since for any pair of minimal elements, like y10 will be bigger than y9, like a lot of the time, most of the time actually. But we can still find balanced elements since, you know, y10 will be balanced with something in the x and the x chain. And this example is also tight. So I think that square root of n is kind of a big barrier since once you get anti-chains that are about the order of n to the 1/2, then maybe there's nothing balanced within them. All right. One other thing I'll say is, so we can define delta sub k of p, and that's, for example, delta 3 of p is the min over all x, y, and z of probably x is less than y less than z. You know, x less than z less than y, all 6 orders of x, y, and z. So that's at most going to be 1/6, for instance. But this condition here and this condition here, these are actually enough to show that delta K goes to 1 over K factorial. I don't know if there's any real desire for that, but we're not just getting 2 elements which are, approximately balanced. We can actually get 10 elements so that every order of 10 elements happens about the same probability. It's pretty. Okay. Yeah.
So there is this theorem that any poset has either a chain or anti-chain of size square root n, right?
Correct.
So, and if you have a anti-chain of size square root n, then you're done by theorem 2.
If we have an anti-chain of psi squared of n, yeah, then we have 1 over e. So yeah, with that, I mean, that's in fact how we get this from this, actually. More specifically, the height times the width is always at least n. So yeah, when you have a big anti-chain or a small height, then you're good. The problem is when you have a small width, it's still going to infinity. Like if the width is like log of n and the height's maybe like linear in n or something, then we don't know how to say anything from these. Okay, so I'm going to introduce a couple of new parameters. When I say new, I think these are all from like Jeff's notes from the 90s, but he never I don't think he's ever published anything with them until now. So the first is pi of x, and that's just going to be the number of y which are incomparable to x. So y is not less than x, y is not bigger than x. So kind of, this is like the degree and the complement of the comparability graph. Our second parameter is sigma of x, and that is the standard deviation. I'll put sigma squared as the variance. Sigma squared is the variance of little f of x, where f, as before, was a uniform order preserving bijection. And our third parameter is the window of x. Maybe the hardest to understand when you first see it. That's the expected value of the minimum of all y bigger than x of f of y minus the max of all y less than x of f of y. These are our 3 parameters. And I'm going to say pi of p is the max given x is in p of pi of x, and sigma squared of p and window of p and define analogously. So how are these parameters related? So I'm going to write, let's write alpha squiggly line beta if alpha going to infinity implies, alpha of p going to infinity implies beta of p going to infinity. All right, well, what do we have? We certainly have that the width of P implies a squiggly line pi. And why is that? Well, pi of P is certainly at least the width of P minus 1. You can take any element in an antichain of size width, and it's not adjacent to anything else in the antichain. We also have sigma squiggly pi. Where does that come from? Well, if we had pi being constant, that would mean that, let's say pi is 100. That means that there's only 100 elements whose comparison to x we don't know. So in particular, f of x must be constrained within some interval of size 100. It can be between, 1,000 and 1,000 plus 100 or something. If that's the case, then that means that the variance is also bounded by some constant. And then it's not too difficult to show that window wiggly sigma as well. So these are all, these are the, I'll say the obvious relationships. So the first thing we were able to show about this, and this is actually, so the crux of this thing, this first condition here, is really just combining probabilistic tools that Kahn-Saks used to prove this first result with something about, I'm gonna write here. So specifically, we showed that if A is an antichain, then the sum of all the windows of X for X in P is omega, right, all X in the antichain A, not in P. Then this is the size of A squared. In particular, if the width is sufficiently large, we have the sum of, so what does this mean? This means that the max of X in the antichain of the window is at least omega of size of A. In particular, this shows this relation here. They have a nice chain actually. The big big width implies big window implies big variance implies big pi. I can actually add a fourth condition on here, which is that if the sum of all the windows of X, or all X in P now. Oops, sorry. Fourth condition here, I like that here. If the sum of all the windows of X for all X in P is going faster than N, so superlinear, then we get at least 1 over E balance. You can probably see how that immediately implies this fifth condition with the help of this. As I said before, this one also comes from this. But that's nice to write down. Okay, so what do we know? Well, I'm going to say our next conjecture, we believe that this going to infinity is enough to guarantee delta going to 1/2. But we believe actually even the stronger statement, strong Kahn-Saks, which is that if pi of p goes to infinity, then that should imply delta of p going to 1/2. This is a conjecture. And Jeff said he thinks it's about a decade after the original Kahn-Saks conjecture, so sometime in the early 90s, or maybe late 80s. But yeah, really, so we're also conjecturing that if the max window gets big or the max variance gets big, that should imply delta going to 1/2. But what we're able to show, so at least the first viewer, this condition here kind of seems, maybe hopelessly optimistic. Just having one element with a lot of comparable things going to infinity seems too good too weak a thing to actually guarantee balance. But what we're able to show is that if Kahn-Saks is true, then that implies that strong Kahn-Saks is true. So somewhat surprisingly, this conjecture is actually not any stronger than our original conjecture.
So Kahn-Saks, if you can,
Not any weaker.
it says just the width,
Just the width.
and this implies you think that if there's an
Single
element
element,
with a
yeah.
lot of incomparables.
Exactly. So how do we prove this implication? Kind of two parts. So our first result, you can see by itself, is if the width of P is less than some constant C, and sigma of X is at least some constant S based on C, and that means that the max of all y in P of delta X comma Y goes to 1/2. I think it's actually, this is based on, there should be some epsilon here. And this is saying this is at least 1/2 minus epsilon. Yeah, so this together with Kahn-Saks tells us that, okay, if sigma of P goes to infinity, then delta of P goes to 1/2. Okay, so how are these parameters? I've already said they're related in this linear form. Is the reverse implication true? Is it possible to have a big window implies big width or not? Well, it turns out not. It's a pretty easy example. It's like a long chain and one element here. This element here will have huge window. I didn't actually define this. So if this is going to be n+1 if X is maximal. So there's nothing bigger than X, then it's n+1. This will be 0 if X is minimal. The window of this element here, this X here, that's going to be n+1, the maximum possible thing. But the width is just 2. So big window doesn't really say anything about width. Similarly, for this one here, if we take 2 chains of equal length, well, then the window of each is going to be O of 1, pretty small. But the elements near the middle, they're going to have sigma about square root of n. So going to infinity. Why is that? If you study like the ballot problem, maybe you have some intuition of why when you're comparing two chains. The middle one, it has some variation in where it can be. Now, this third one, well, certainly, if you look at this element here, this element at the bottom, that x, this element has large pi, but small sigma. So at least we can have pi of x going to infinity and sigma of x O of 1. But it turns out that what we can also show is I'll write it like this. Pi of p squiggly sigma of p. This is probably our nastiest result. So fairly tedious, but so we're saying that when pi of p is big, so when there's some element in the poset, it's incompatible to a lot of things. Well, that element itself might have small sigma multi deviation, but some other element in the poset must have sufficiently large sigma. All right. So hopefully you can see as pi of p goes to 1/2, then okay, so as pi p goes to infinity, then that means sigma of p goes to infinity as well. And we already said as sigma of p goes to infinity, then this says the delta goes to 1/2. So delta, so okay, so pi of p, yeah, so that means the Kahn-Saks implies a stronger Kahn-Saks. This is quite surprising. Great. How much time do I have left?
Basically 5 minutes.
Okay, yeah, I think I'll just get into a tiny bit about how we prove these things.
If you need a few more minutes. it's all. You want to show us something from the proof of theorem 1 or 2?
Yeah, well, I want to get to where this 1 over e thing comes from specifically. So I'm going to say let O of p be this polytope. It'll be the set of all W whose indices are between 0 and 1 indexed by elements of p, so that W of x is less than or equal to W of y when x is less than y. This is the order polytope. If I want to look at the order polytope intersected with the half plane given by Wx is less than W of y. And I do this over just the volume of OP. So by the way, I'm writing absolute value signs in the volume of polytope. Feel good with that. So this is actually just the probability that x is less than y. Well, another thing about the order polytope is the centroid of the order polytope. That's just going to be a point C, so that C sub x is equal to h of x over n plus 1. Okay, so if h of x is equal to h of y, what does that mean? That means that probability of x less than y That means it just, this half plane, the hyperplane goes through the centroid here. So as a result of, I think it's Grunbaum from 1960. And then it was proved again later, but it says if H is a hyperplane going through the centroid of P. I think we need some sort of like P's like a convex compact body or something, but don't worry about that. Well, then that means that any half plane, so half base on one side of H intersected with P over all of P is at least 1 over E. So together with this, what that implies for us is if H of X is equal to H of Y, and that means that delta of X and Y is at least 1 over E. So where do these things come from? It's 1 over E minus little of 1. Well, it's basically taking this idea and trying to relax it a little bit. So we can't guarantee that the centroid, H and X, X, Y are going to be exactly the same. But for instance, if we can show that they're sufficiently close, that will mean that delta is almost 1 over E minus little of 1. So that was the idea of like, that was Friedman's original idea. Our contribution was trying to combine that idea with this idea of window. So what we showed is if, let's say the window of X is much bigger than this distance H of X minus H of Y. So Y is much closer to X than the window is. That implies that delta of X comma Y is at least 1 over E minus little o of 1. And basically, the proof of this kind of follows along similar lines as this thing. Yeah, so that's, you know, look at a paper if you want to know more about that. For any more things from here, like this one comes from a geometry argument as well. Yeah, okay, thank you. I think that's all.
Any questions, comments?
I have some meta question. I mean,
Yes.
you argue many conditions that if they happen, then that is big.
Mhm.
And it looks like if you want to sort a set, then at the beginning, this condition will hold, and at some point it will stop holding. And so, do you know if you sort it at what point it stops being true? I mean, I would hope that you have little of one of the time to be that they will not hold.
For what we showed, or
Yeah, for example.
well, okay, I mean, I'm not sure how interesting this is in the first place to the sorting problem, since what Jeff and Mike already showed is that you always have a sorting thing at least 3/11, for instance, and that gives you O of log of E P queries be sufficient. What we did, we give like a slightly better, sorry, if you can get to 1/2, that would be a better constant in front, I guess, but yeah, like for example, we know that there exist posets requiring something like 1.4 times log base 2 of E of P. So the information bound isn't actually typed. We're not really gonna get down to exactly one. Yeah, so I'm not, does that have answered? If we knew that the window, so if we knew that width of P being sufficiently large implied that we could say something as, okay, keep removing elements, width of P is still large until you get down to width of P being bounded. And then when width is bounded, that means the number of linear extensions is linear as well. So I don't know, maybe there's something there. Yeah,
In all of this line of work, the poset that you were given has a linear extension.
yeah, every poset has a linear extension.
Right, so what if you have, so I can think of it as if there was a chain and someone erased parts of the information and.
Yeah.
And that's what you were doing. What if there is some other poset that we all know and then someone erased part of it and that's what you're doing? Is there any work?
So how I'm imagining this is you're given some comparisons and you want to do some queries to determine the original poset.
Right.
Yeah, so
Maybe it's in the family of posets that we know, like a chain, but could be others.
there's like this dual problem of rather than trying to start with a poset and you construct the chain, you can start with an anti-chain and you want to construct some sort of poset or some sort of poset. How many queries does that need? So for instance, I don't know if you know the problem of trying to find a median of a bunch of elements. What is the median? That means you're trying to do enough queries so that, let's say you have like, 101 elements. You want to know that this element X is less than 50 things and bigger than 50 things. So finding the median is actually a form of, you're not trying to like manufacture a specific coset, starting with nothing. So they're like, combinations of these two things where I give you a poset, you want to make your poset, how many queries do you need to ask to be able to guarantee that at the end, your poset contains, or the poset you get contains what you want to start with. And yeah, there are versions of that which are close to the information theoretic bound in this way. Well, I guess that's not quite what you asked. Yeah, I don't know anything specifically where I have a hidden poset and you want to find what it is. Be an interesting problem.
Questions? Okay, thanks so much.